Our next talk is from Hulu. It's on video recommendation from relevance to reasoning.
Thank you for introduction. Hi, my name is Larmin. This talk is supposed to be given by Xiaoran, but he can't make it because of visa problems, so I'll be presenting on behalf of him. If you have any question that I can't answer, please give him an email. This talk is a joint work with Xiaoran, Songpeng, and Han. And the topic is video recommendation in Hulu from relevance to reasoning. Okay, in case some of you might not have heard of Hulu, Hulu provides premium live and on-demand channels to more than 20 million subscribers in the United States. It is a joint venture with Comcast, the Walt Disney Company, 21st Century Fox, and Time Warner. We have more than 500 content partners and 1,000 advertising partners. In Hulu, we have two user scenarios, the store shelf and the autoplay. The first requires a list of videos to maximize the chance that the viewer would pick one of them to watch. The second requires a sequence of video recommendations that the viewer would continuously watch within the current session. So we designed specific models in the model layer to match with each user scenario. We use a deep neural network to to calculate the relevance of items in the store shelf scenario, and we use a recurrent neural network model to predict the next video that the viewer is going to watch. We incorporate Thompson sampling to balance between exploitation and exploration, and a determinantal point process model to balance between relevance and diversity. The determinantal point process work is accepted as a poster in NIPS this year and will be represented by me. Please stop by if you have a chance. In the feature and data layer, we train embeddings for content, user, and context information. For example, to train content embeddings, we collect factual text from metadata, keywords from descriptions, and objects or actions recognized by using computer vision techniques. In recommender system community, recommendation algorithms based on matrix factorization and factorization machines have been very mature. In recent 10 years, the rise of deep learning has brought in many powerful techniques, including word embedding methods such as skipgram, word embedding methods such as deep path and transee, and other embedding-based methods, which can be roughly viewed as highly nonlinear extension of matrix factorization. As we recommend more relevant items to users, the need to understand the latent factors in the recommender systems has become more and more important. Not only in the recommender system, but many machine learning models need to become interpretable, at least in some way, to tell people how the decision comes out, rather than just showing a result from a black box. For this end, we go back to logic reasoning, which offers both predictability and interpretability. In logic programming, we are given a set of predefined rules and a database of facts. And our purpose is to use them to predict a goal. For example, we try to predict George and David are friends. Then we need to search for the rule head matching predicate friends, and then substitute the variables with constants George and David. And then we go down the tree to search for facts matching likes George C and likes David Z. We can see that the whole process is a search. When we successfully reach the leaf, we prove the goal by the proof tree, which offers very detailed information about the proof. Of course, there are obvious this methodology has obvious drawbacks, which is requiring handcrafted rules limiting its expressivity, and the whole procedure is not trainable, which means it cannot adapt to data and be trained end to end. Recent works on reasoning focus on developing differentiable graph-based reasoning. The main purpose is to apply gradient-based or end-to-end training and learn soft logic rules characterized by weights. In this way, we can utilize many recently proposed deep learning components as building blocks. Compared to traditional logic-based reasoning, differentiable graph-based reasoning formulates the reasoning problem into path search problem in a given knowledge graph. There are many ways to model differentiable reasoning. Then we can use predefined rules and these learnable ways to adjust their importance as in the TensorLog paper. If no predefined rules are available, are not available, then we can learn them from scratch as in the NeuralLP paper. In our work, we formulate the rule learning problem as a graph-based reasoning program. Our definition of graph-based reasoning program is based on logic programming, but from a graphical perspective. Given a graph and a goal predicate with two variables x and y, we construct a connected subpath linking the source node x to the destination node y, which is a set of selected edges to support the goal predicate. It can be viewed as strong interpretation why the destination results from the source. As the whole process attempts to predict the destination as well as possible. To describe the interpretation is good or not, we list the 3 points: connectivity, focusing, and saliency. To illustrate the 3 points, we give 3 bad cases. The first example tries to find a bunch of nodes to link Ironman to Ant-Man. For the prediction accuracy, covering more relevant nodes often leads to higher accuracy, but for interpretation purpose, it will overwhelm users and produce useless results because humans prefer reasons to be focused on few key points. The second example does not construct a connected path from Ironman to Ant-Man, making the interpretation nodes less relevant. The third example provides connected and more focused path from Ironman to Ironman 2, but the intermediate nodes are either an actor playing a small supporting role or a general category such as sci-fi, failing to find more significant nodes such as the leading role actor, Robert Downey Jr. The graph-based reasoning program has many real-world applications. The learned interpretation subgraph can also be written in the language of logic rules. For example, in the classification tasks, the reasoning program would find significant features linking the entity to the corresponding label. In the recommendation tasks, results by calibrative filtering can be interpreted by the pattern. The user has bought another item which is brought by another user who buys this item. And the item-based methods finds a path with the pattern. The user has bought another item which is similar to this item. In the information retrieval, to return a relevant document by a query, the reasoning program would find the pattern query word document. From the graphical perspective, a graph-based reasoning program actually produces a belt, a subgraph linking the source node to the destination node. We can think of the belt as a wide path envelopes several relevant paths. Based on this intuition, we introduced attention mechanism and proposed a new concept called attention belt, which models the reasoning process starting from the source node and ending at the destination node. if we treat the reasoning process as some kind of dynamics of attention flow, the attention belt is a trace recording how attention transfers from the source to the destination during reasoning process. Note that in the attention flow, the attention is a limited resource, which means the total amount of attention is fixed. Here we assume that the total amount of attention sums up to 1, which is a probability form. We define two types of attentions, focused attention and flowing attention. The focused attention represents attention aggregated on each node, and the flowing attention represents attention going through a directed edge. The relation of two types of attention involves a transition matrix. It is analogous to random walk, but the difference is that the transition matrix P here changes at different time steps. We also define another kind of flow called information flow, implemented by message passing in graph neural networks. There are 3 key steps in message passing. The first step is aggregate messages from neighboring nodes. The second step is to update node states based on the incoming aggregated messages. Step 3 is to emit new messages from each node. Different from many message passing algorithms, with that, the two kinds of flows, attention flow and information flow, affect each other. First, with that, attention flow affects information flow. When aggregating messages from neighboring nodes, we multiply it by the flowing attention on this edge. And then we let information flow affect attention flow. The transition matrix P is calculated based on current context information. Actually, there are many ways to compute the transition matrix based on current node states and their relations, the relation of pairs of nodes, such as the bilinear form or a typical MLP, which takes the concatenated node states and their relation as input. The iteration does not need to reach convergence. Normally, we iterate the whole process by several steps, and as our purpose is to build an end-to-end training and backpropagate the gradients through iterations. To train our model, we design a cross-entropy loss based on final attention distribution, which represents the final probability to predict the destination. We found that attention flow over the graph is a natural way to do the normalization. Therefore, there's no need to compute softmax, and there's no need to do negative sampling. There's also a guess that gradient flow, that gradient might flow backwards through attention flow more easily than through highly nonlinear and interfered information flow. Our work is still in progress to make the attention flow more interpretable. There are some possible ways to try. The first is top K attention, which forces attention focused on few key, on most relevant nodes. The second is jump back and stay still attention, which protects attention from getting trapped in irrelevant but connected path. The third is to treat attention as a discrete action in reinforcement learning. For future work, there is an alternative way to, which is stochastic graph-based reasoning, where attention is binary and sampled, like a discrete action in reinforcement learning. This kind of attention are kind of a hard attention instead of soft attention, which might make attention more focused and more interpretable. The key challenges here is that the whole learning system becomes non-differentiable, and we cannot apply standard backpropagation directly. We found some clues to solve this issue from reinforcement learning, but we need to figure out a way to to implement IL-based approaches in a graph setting. Then we propose a generalized backpropagation framework called backprop-Q, which extends transported learning signals beyond gradients between stochastic nodes while preserving the benefit of backpropagating gradients through deterministic nodes. This framework is described in this paper. And this concludes our work. Thank you. And if you are interested, please come back. Thank you.
Are there any questions? I had one minor, actually, question. So I noticed when you're talking about the graphs and you're saying you're going to learn the weights, but it looked like the edges are predetermined already. Like you have you had a slide up with talking about relations with is a Avenger or has a high-powered suit. So how do you get that information? Is that inputted manually, or do you learn that? Or?
Yeah, the relation is from metadata. We have them provided by our content partners, and they can give us that, and we can build a knowledge graph based on the metadata.
Excellent, thank you.
Thank you. If you are interested in, if you have more questions about Hulu, please find us in the booth. Thank you.